Having studied the balancing of rotors in the last two lectures, in this lecture we will start um, our study of balancing of IC, internal combustion engines. To start with single cylinder. So, in the dynamic force analysis of the cylinder crank, we made these points earlier. That is, the connecting rod is approximated by two coil muscles, one reciprocating with the piston, executing only sliding motion, and the other rotating with the crank, executing only rotary motion, which simplifies their dynamics. Then the crank mass, including this big end from the connecting rod, is provided with a sufficient counterweight to force the center of mass of the whole thing right at the fixed pivot point, so that the CG of the so-called body does not move. So inertia force gets out of the business so far as the crank is concerned. Now, third thing that we studied and discussed there is that we were making most of the analysis for the crank speed to be constant, and practically that is to be ensured by drawing average turning moment from the engine equal to whatever is the load moment, okay, over cycles, so that the speed does not go on increasing or go on decreasing. And then the question of the variation of instantaneous speed within a cycle was sorted out by mounting on the crankshaft a flywheel of sufficient inertia to keep omega constant within a cycle. Now, this width is supposed to be within, not within. Okay. So, these things we keep in mind as we continue the study of that same mechanism. See in this diagram all the forces and moments on moving wings as well as on the frame. That is all the wings together. Now, the forces on the moving wings I have shown with a simple arrow, and the forces and of course moments on the frame I have shown with this thick arrow with double line, like it implies that kind of side. Okay. So here you have the gas, hot gas, I mean hot after combustion, which has a pressure, and it applies the same pressure in all directions. Now, at this end, or the left end, as the figure shows, this force, the pressure into the area of this cross section area of the cylinder, PA, operates on the cylinder. That's why it is fatter, and on this end, at this end, it operates on the piston. P. Then the connecting rod pulls the piston or pushes the piston like this. I mean, sometimes it will pull, sometimes it will push, but we are taking this reference as push. As Q, okay, that force is Q acting at the CG of the piston, and some of it, one component of it will act on the frame like this downward, and because that way, that in that direction piston doesn't have freedom to move, so in that direction that force will act on the frame pattern, and as the normal reaction, it will apply a force on the piston upward. Okay. Now, this piston, since it is getting a force Q from the connecting rod, it will also give an opposite, equal and opposite force at the same point, which has not been shown here intentionally, because connecting rod we are actually no more considering as a body. What consideration? Because that rigid link has been reduced by our approximation to two masses, one at this end, which has been taken care of in the piston mass, and the other at this end, which will be taken care of with the crank mass. So connecting rod has nothing left. It's a massless rigid long body. So we know that if it is massless, there is no inertia force there. So we can consider the force balance as it is simply. Okay. So this force will be the same as this force. So the way the force from the piston on the connecting rod has not been shown at this end, similarly the force from the crank on the connecting rod is also not shown. It is clear that whatever force the piston applies, that is negative of this Q, gets transmitted through the connecting rod to this end without any flux. So this is the force Q in this direction on the crank. What are the other forces on the crank? Reactions here, horizontal, vertical. So horizontal reaction RH, leftward has been shown because that is a positive direction, and vertical RV. Okay, here it is not. It has not been shown in the positive direction because we have a sense in which direction. Okay, it is not. The RH also has been shown leftward, not because that is not just because it is a positive direction. That is because we know that it will be in this direction. If Q is pushed, okay, this way, okay, then its horizontal component, I mean, its reaction, you see, RH and RV are reactions. So this way and this way. So in this diagram, the practical and sensible directions have been used, not necessarily for algebraic sign considerations. No? So in some configuration, it will be the other way around, but then the numerical value will show up. So now this reaction is from the frame. So on the frame, equal and opposite forces act. RH on this direction, in this direction, RV upward. And then on the crank, a moment or force is MR. There is a load moment, which the moment of this Q force, which has come from the connecting rod, will overcome. And overcoming that moment is the job of this moment. Okay. So now this is not a free body diagram because here all the forces and all the bodies are shown together. Now we free one body at a time, except the connecting rod, which has nothing to do with it. So first the piston. All the forces on the piston are shown here. And we consider the vertical force. So M upward, Q sine phi downward. So there you go. Then Q cos phi leftward, PA rightward, and this inertia force leftward, because now this is because it is a reference direction, reference positive direction. But inertia force itself has a negative sign minus mass of reciprocating parts into x W. Okay. So you could say that M REC x double dot rightward. So that it gets added to PA. So PA plus that is equal to the leftward force Q cos phi. Okay. So these two we get from the piston force balance. Moment also must be balancing on the piston, obviously, because piston doesn't have rotary freedom, so nothing can show up as inertia in that. rotational motion, and how that is achieved. See, one way, the theoretical way to say that the resultant of this distributed force PA passes through the CG, Q also passes through the CG, normal reaction also passes through the CG, and there is no clear cut moment applied as it is. So that's it. Okay. But actually, what happens that whatever little eccentricity of this force, some other manufacturing tolerance related uh, contact that should not have taken place, if a force at one point, its reaction appears from the other, and so any moment that could come because of any eccentricity of any force at any instant gets balanced by the lack of field. So moments are balanced, and there is no point in taking that into account here, because how moments are balanced, nobody knows the right details of that. As long as we achieve it by the physical construction, we are true. Now, these are the two equations that we have got from the analysis of the piece. Now, connecting rod we don't bother because this Q equal to this Q has already covered its levels or statics, if you like to say. Now, we take up the crank. So, crank here, force Q, force RH, force RB, moment M. And inertia force, because the CG does not know. CG has no acceleration. So the forces are on the crank. So RH leftward is equal to Q plus pi backward. Similarly, RB is Q sin phi. And MR is equal to the moment of Q. And how to work out the moment of Q? Q into the perpendicular distance of its line of action from the fixed point. Look at here. So, since this position OP is x, this angle is phi, so the perpendicular distance will be x sin phi. So, Q times x sin phi. That's it. And now you see this n is Q sin phi, which is RB. This thing is Q cos phi, and therefore RH. So, it is. Now comes the frame. Frame is this. Upper part has not been shown because all the forces have been shown on the lower part. PA here, this normal reaction here, RH here, RV here, and the moment against this, the reverse moment, equal and opposite MR. Now consider all the three equations from here. Frame also doesn't move, so inertia force gone. So horizontal force balance. So sum of all the horizontal forces, RH in this direction and PA in this direction. So RH minus PA, okay, PA minus RH. So that is the first direction. PA minus RH, PA minus RH. Fine. So PA minus this is RH, Q cos phi is RH, will be minus M rect. So this is minus M rect. Okay. Then take the vertical forces together, and that is RV minus M, RV minus M, and RV here and M there, both are equal to Q sin phi. So that's C. Now all the moments about the point O. So this N acts at a distance x. So Nx, and the direction of N and the x are perpendicular. Is perpendicular. So angle between them is 90. So Nx anticlockwise, Mr clockwise. So Nx minus Mr. Now Nx will be Qx sin phi, which is same as Mr. So this is 0. So now you see that on the frame, when you look at the unbalanced forces and moments, you find that there is no unbalanced moment and no unbalanced vertical force, only unbalanced horizontal force like this. Now I am calling it horizontal. What we really mean is that along the direction of motion of the piston, along the center line of the cylinder. If it is a vertical engine, then that will be vertical. And don't think that you have to bother about gravity because it will be vertical. You don't have to bother about gravity because gravity load is not dynamic. It always stays constant acting in a particular direction. So you don't have to bother. For that matter, here also, while considering the vertical forces, we did not bother about weight. Okay. Neither in Japan. We are talking about mass for inertia, but not for weight. Because weight is not a dynamic force. What do you do with it? Any structure has to support it. Nothing big, no big deal in the machine. So the only unbalanced force and no moment on the frame is this. We will bother about this. And at this point, give me a small half a minute break, and I'll come back to you quickly. So the unbalanced inertia force Fx turns out to be this. So if we recall the expression of x double dot from our earlier study of dynamic force analysis, it's minus omega square r into this whole thing. You would recall that this A2 is simply lambda, and then A4 other things you can find out. Of course, A2 is simply lambda, that is an approximation. Okay. So similarly, you have an approximation of A4, A6, etc. So this turns out to be the unbalanced inertia force. About balancing which we may like to think something. Now we call the magnitude of the primary force, we call as the magnitude, or we call as the magnitude of the primary unbalanced force as this. The cos theta is actually not just the direction, in a way it is the phase. So as theta changes with time, so the because direction of the force is anyway along the cylinder axis. Okay, so the this cos theta cos 2 theta term does not give really the direction as such of the unbalanced force. It gives the phase. Okay. So the magnitude is this of the unbalanced force, unbalanced primary force. Okay. So we call it like this. And similarly, the magnitude of the secondary unbalanced force would be A2 times this. And as you recall, that a good approximation of A2 is just lambda. So you can put lambda here for approximation. Okay. Ignoring the terms in the series for A2 from lambda cube onwards. The lambda square term is anyway absent from there. So you could think of the next harmonic, which is cos 4 theta and so on. So, but that becomes too small in magnitude because the term here that will come will be less. Okay. So our primary purpose would be to balance this part and this part equally. So the forces would be this so-called magnitude into cos theta, so-called magnitude into cos theta, and so on. That's why we call them harmonics. So completely balancing this unbalance is almost impossible and certainly impractical. You will find in the textbook a little funny way in which it can be balanced. This force can be balanced if one wants. And the way to do that is to extend the connecting rod further and put a mass here first, such that this mass, the extension of the connecting rod itself, and this whole thing, piston assembly, the whole thing it has its CG at this point, at the crank pin, okay, where crank and connecting rod connect. And then that entire mass and the crank mass together is provided a sufficient counterweight so that this whole thing situated here and the rest together has a CG at this, which does not move at all. So that way, in principle, you could balance it, but imagine how much of extra heavy mass you have to put in order to handle all. It's not practical. It's not what to do. The practical solution is partial balance. That is, this m rect omega square r etc. So that basically amounts to something like a mass m rect here rotating about this point. Because if there were a mass at this point called m rect, okay, its rotary unbalance would be a force in this direction equal to m rect omega square. If you put a counterweight corresponding to that, that is already for the crank mass you put a counterweight. In addition, put another counterweight m prime at a distance r prime, so that you have this backward loading of m prime r prime, giving a balance to that. So now the complete thing to balance the horizontal force unbalance using this reciprocating part by this would be to ensure that m prime r prime is equal to m rect into r. But then that counterweight would produce a vertical unbalance also, which would be the sine component. Okay. So you don't, because sine theta also varies from -1 to +1. Cos theta also varies from -1 to +1. In order to completely balance one, you produce the other completely, which remains unbalanced. So that you don't like. So what you do is a partial solution. Partial. So m prime r prime you don't want equal to m rect r. You want a little less. So that the remaining horizontal primary unbalance is m rect r minus this thing into omega square cos theta, and the corresponding vertical unbalance that gets created because of this extra counter mass, that is n prime r prime omega square sine theta. So this is the cost of this reduction here. So you work out what fraction of m rect r should m prime r prime be, so that the resultant of these two is less, or some sort of it. So you work out a suitable kind, so that m prime r prime is pi fraction of m rect r by itself. So this is what is a partial balance, and this terms of that is a practical solution, as long as you insist on using a single. However, you can say that no, we will do multi-cylinder. Typically, big engines with large capacity, large load, etc. Operate on multi-cylinder. So a lot can be studied in that, but we will study only. There are several kinds of multi-cylinder engines. One is inline engines, in which the several cylinders with their respective pistons are aligned in parallel lines all in a way, and they all feed to a single tank which is in the perpendicular direction. And the single crankshaft basically. But then in the case of inline engines, the crankshaft and crank together is built integral. Okay. In any case, they are supposed to be rigid with each other. Okay. So with the crankshaft must rotate. Now here the crankshaft is built with several bends in several directions, so that these bends operate as the corresponding cranks, and they are typically out of phase. The phases of the different cranks in different directions, putting them in different directions in the perpendicular direction of the shaft, you achieve their power strokes at different time intervals, so that overall some sort of a balance is achieved. Another way to work out a multi-cylinder engine is a V-twin. This has just two cylinders, one along this arm of the V and the other along this arm of the V. The angle between the two arms is something which may vary from design to design. So this is typically a two-cylinder. So in a V-twin engine, what happens? That unbalance in one direction corresponding to one cylinder and unbalance in the other direction corresponding to the other cylinder, both have one component opposing each other which balances. The other components, of course, will add. But then having a single cylinder engine with a particular capacity, which means a particular unbalance for that matter, compared to that, if you split it into two smaller cylinders, two corresponding less power giving piston cylinder alignment, such that their unbalances partly balance and partly sum up together, that is relative advantage. So that is how what V2 engine gets as advantage. If you extend this idea, why two? Why stop at two? Let us have five, let us have six, and put them radially at this much angle, another that much angle, another angle, another angle, another angle. Then you have radial angles. And the number of cylinders are organized in different radial directions in the same plane. You see, V-twin engine and radial engine are in the same plane, not in line. Okay. So inline engines are to be balanced in the spirit of a proper big full rotor, that is forces and moments all together you have to consider. In the case of V-twin and radial engines, it's a single plane. Okay? In a single plane in different radial directions, you will have the cylinders and therefore the unbalance. So in all these multi-cylinder engines, these are the points on which one focuses when one studies, analyzes, or decides. One is arrangement of tanks and cylinders. In the case of actually the arrangement of tanks is not a big idea, because In radial and V2 engines, it is the same time. In the case of uh, inline engines, though for the namesake they are different times, but since they are built integral with the crankshaft, it turns out to be the same rigid body. So it is a geometry of the crankshaft and the crank, okay, in that case. And the cylinders, that means the cylinders in their relative geometric dispositions with the common crankshaft. This is one important thing. And intimately connected to that is the firing order. In which order you fire the different cylinders. Of course, you can fire it only at that time when the compression is complete, okay, where the air fuel mixture is compressed. Then you can start the initiate the combustion for appropriate thermal advantage. So, and the order of the cylinders to be so fired is another point of focus, and that has a very close connection because of the necessary moment in the cycle when the firing should happen. Now, as a result of this arrangement and this firing order, you would get power from different cylinders at different points of time, and as a result, the non-uniformity of power that otherwise results in a single cylinder engine would be to a good extent reduced. And that is another point of focus which an analyst or designer would like to study. And its effect on the turning moment diagram, it would not be so uneven. And most of the time, the moment generated by the engine as a total in its entirety will be relatively closer to the load moment than in the case of a single cylinder. So these are advantages. And so far as the way of analysis is concerned, there is some analytical artifact which is put in practice. So we try to either balance or study the unbalance of the primary turn in the unbalanced force of all the cylinders together. That is, all the primary unbalanced forces, they are balancing their unbalanced magnitude we try to consider together. And that we consider as a primary term. Take only the cos theta and not the cos 2 theta, cos 4 theta. And then, as if that is the only term that comes out, okay, and calling it a primary term, we study its unbalanced. And then we say that rather than considering the cos 2 theta term as a secondary term coming out of this time itself, physically, we pretend as if it is another time, a fictitious one, okay, which is rotating at the twice speed. Okay. So obviously, then in place of cos theta, you will have cos 2 theta. So that we consider as a secondary crank, as if it's a different crank, rotating at speed twice. And then we pretend as if we are studying its cos theta, which in this case happens to be cos 2 theta because the speed happens to be that. So that way, some of the analysis becomes more practical. You will see that in the analysis and examples in the textbook. With all these things in mind, we study the extent of elimination or reduction of primary and secondary forces and moments separately. Primary force, primary moment, secondary moment. What happens to these quantities for the entire. So these are the points of focus in the study of multicylinder. So this is a lot for study, but not much of it can be done in a classroom setup. So it needs to be studied and done by the learner. So my advice is that study the solved problems 7 to 5, 7.5 to 7.10 along with the associated relative theory. The same process followed in most of them with slightly variations over these pages. So study solved problems, and in the next lecture, along with balancing of linkages, if time permits, then we will take up one example of one of these, one example of all of them together. I mean, not all of them together, one example of one of these. So, how to handle multiple engines and what are the things to analyze, which makes sense, which is relevant, which is really what is going on. Okay. So, we'll take one example of multiple engines in some time in the next lecture. The main new topic in the next lecture will be balancing of linkage.